Yeah, hello, sir.
Shall I start?
Okay, sir. I will start from here, sir.
Okay.
Yeah, sure. So, good morning, Dr. Rajaraman, and good morning to the participants who are watching this live session. So, ladies and gentlemen, and welcome to today's session on advancing scientific modeling wavelet methods for solving complex mathematical equations. We are thrilled to have you join us as we explore the fascinating world of wavelet methods and their role in addressing complex mathematical challenges. Whether you are a researcher, an academic, or someone with a passion for scientific modeling, this session is designed to provide fresh insights into how wavelets are changing the way we solve the problems. So, wavelets have become a powerful tool across the various disciplines for their ability to analyze the data at multiple scales and making them particularly effective for handling the intricate and nonlinear mathematical equations. And today, we will delve into the core principles of wavelet theory and explore its wide range of applications and demonstrate how it can be leveraged to solve real world problems in field like engineering, physics, and data science. And by the end of the session, you will have a clearer understanding of why wavelets are becoming such an essential part of modern scientific modeling. As we move through the session, we encourage you to engage with the material, ask questions, and share your own experiences. So, our aim is to create a dynamic learning environment where we can all deepen our knowledge and spark new ideas. And without further ado, let's dive into the world of wavelets and see how they can advance our understanding of complex mathematical equations. And before we start Dr. Rajaraman's session, I would like to give some short introduction about him. So it's my great pleasure to introduce our guest speaker today, so Professor Dr. R. Rajaraman, a distinguished mathematics professor from Savita Engineering College in Chennai, Tamil Nadu. With over 25 years of experience in academia and research, and Professor Rajaraman brings a wealth of knowledge in nonlinear and fractional differential equations and mathematical modeling and wavelet methods. His expertise in these areas has earned him recognition as a research supervisor in mathematics by Anna University and solidifying his position as a leading figure in his field. So, Professor Rajaraman's career has spanned a variety of esteemed roles, including his time as associate professor at Savita School of Engineering and professor at Bharat Institute of Higher Education and Research in Chennai. His teaching and research have made a profound impact and guiding both undergraduate and postgraduate students through complex mathematical concepts, even incorporating online courses to expand his reach with an impressive body of work that includes 27 international publications and 17 of which are indexed in Scopex and 8 in SCI. His research contributions have garnered 138 citations and highlighting the significance of his findings. And currently, Professor Rajaraman's research focuses on fractional wavelets and fractional differential equations, where he applies innovative approaches to solve complex problems related to chemical, biochemical, and biological physical phenomena. His profound insights and experience make him the ideal speaker for today's session. So we are honored to have him with us, and I know we all benefit from his deep expertise and passion for advancing scientific modeling. So please join me in welcoming Professor Dr. R. Rajaraman. And before the session, I would like to give a short intro about our services at Tech Solutions as pioneering research venture. So our company is dedicated to developing innovative engineering, management, and scientific tech solutions tailored to support your ecosystem with our forward-thinking approach. We pride ourselves on offering affordable services and robust support and backed by a professional and skilled team ready to deliver exceptional business plans. And Temstick Solutions specializes in a comprehensive array of services, including digital marketing, web designing, server management, on-field marketing, Android and iOS app development, telecommunications, AI tools, SEO, and web analytics. And we also excel in business operations and process automation across the various sectors, such as industrial research, mechanical and automobile, aerospace and defense, electronics and energy, architecture and civil engineering, medical applications, maritime and marine, agriculture and textile manufacturing, and more. And additionally, we are passionate about education through Mastering Up, a free platform aimed at unlocking skills for a brighter future. We invite you to join us in empowering young learners by sharing your knowledge and expertise. So, our guest lectures foster skill development, knowledge sharing, and personal growth, and offering a platform to inspire, educate, and connect with an enthusiastic audience eager to learn. So at the end, I would like to introduce to the motto of Dr. Rajaraman session. So in the pursuit of knowledge, strive for precision, innovation, and the relentless applications of mathematics to solve real-world challenges. So I would like to hand over the session to Dr. Rajaraman, and also thanks a lot for joining us today. And over to you, sir.
Thank you, ma'am. Good morning, everybody. I am Dr. Rajaraman, Professor of Mathematics, Savita Engineering College, Chennai. And Madam introduced about me, everything. So we now start our discussion now. We are going to discuss on advancing scientific modeling, wavelet methods for solving complex mathematical equations. Here we are going to focus on the reaction diffusion equation, which plays very important role in science and engineering. In science and engineering, reaction diffusion equations model many physical problems. Okay, why we need wavelet? What is the importance of wavelet? If the differential equations are linear, we can easily solve by many analytical methods. Those are basically engineering students who studied many analytical methods to solve the linear differential equations. And also then we can apply Laplace transform, Fourier transform also to solve the linear differential equations. And when the equations are non-linear, it will become more complex. Then we can only you apply the numerical methods, Rangi-Kutta method, Euler method, all this method to solve the differential equations. But they will give only the approximate answers. So in between them, we can apply wavelet method, which will give the best solution, nearing to the exact solution of the differential equation. By we can check it by comparing it with the experimental values. Many physical problems have the experimental values in laboratories, and we can solve the mathematical model using these wavelet methods, and we can compare the solution. The error is very low, so they are very nearing to the exact solution. So they will give the accurate solution. Wavelet methods are giving the accurate solutions, and we can also compare the wavelet methods to the semi-analytical methods. Homotopy perturbation method, homotopy analytical method, analysis method, homotopy analysis method. Many methods are there. Adomian decomposition methods, and they will give the very accurate solutions. We can compare the wavelet methods to the those methods. Why we need wavelet methods? Already we have semi-analytical methods. Why do we need the wavelet methods? Because we can solve the complex different nonlinear differential equation without using the difficult integration and differentiation. By making the differential equation into the algebraic equation, then applying the numerical method, we can solve the algebraic equations. Now we can start our. This is the outline of my speech. Uh, what is ODE, what is PDE in phase one, then fractional, what is fractional differential equation, then what is reaction diffusion equation, then we move to the wavelets, what is wavelet transform, genesis of wavelets, origin of wavelets, classification of wavelets, and multi-resolution analysis. Then wavelet methods, what are the wavelet methods available, and analysis, and how can we apply to the wavelet methods to solve the mathematical models and results. And then comparative study. Comparative study means we can compare the results with the exact solution and the solutions of the semi-analytical methods. This is simply a flow chart. You can view this. Differential equation is are broadly classified into ordinary differential equation and partial differential equations, and here reaction diffusion equation we consider, and here the equations: nonlinear differential equation, singular boundary value problem, fractional differential equation, reaction diffusion convection equation, mathematical modeling, and some reaction diffusion equation, what are Lamb-Emden equations, Michaelis-Menten enzyme kinetics, Fisher's equation on population growth, Vitus-Nagumo equation on neurology, Murray convection equation, Flimford diffusion model. The many reaction diffusions are there. They are what? They are modeling the real physical problems in science and engineering. And many methods and wavelet are available. Chebyshev wavelet method, Legendre wavelet method, now Hermite wavelet method, Bernoulli wavelet method, many Lucas wavelet methods. Many wavelet methods are available. There are two types of operational matrices we are applying in the wavelet methods: operational matrix of derivatives and operational matrix of integration. Okay. Now, I think basically everybody knows those who studied the mathematics degree or engineering degree, the basic form of the nth order differential equation: a naught into the d power n y by dx power n plus a1 into d power n minus 1 y plus dx power n minus 1, etc. Here y is the dependent variable, x is the independent variable, and a naught are the coefficients. It may be constant or variables. Okay. And linear second order PD is given here. AUXX. UXX means dou square U by dou X square. And PD means what? There are two independent variables, two or three independent variables with a single dependent variable. We can differentiate with respect to one independent variable, keeping other independent variable as the constant. That is the partial differential equation. B into dou square U by dou X dou Y. C into dou square U by dou Y square, and etc. This is the form of the general PDE. Many of you know about that. Those who studied engineering or basic mathematical degree, BSc. Okay. What are the applications of this ODE? Why we are studying the ODE? What are the applications? Logistic growth models, species population considering limited resources, predicting species or bacteria growth application, radioactive decay used in radiocarbon dating and medical treatments, in electrical circuits applied in electronic signal processing and control systems. And these physical problems are modeled as a ordinary differential equation with the initial or boundary condition. Initial and boundary conditions are very important. Then only we can solve the physical problems. And heat conduction equation, many of you may know heat conduction equation. The temperature distribution in a one-dimensional rod, dou U by dou T into D into dou square U by dou square. D is the diffusion constant, Fickian diffusion. And this is the one-dimensional heat equation. Two-dimensional heat equation also there. Dou square U by dou X square plus dou square U by dou Y square is equal to 0. Laplace's equation. The heat diffusion in a rectangular plate. Okay, these are basic examples of the these are the reaction diffusion equation. These are ordinary. This is a PDE. PDE is the real world application of PDE in thermal insulation and heat exchangers and electronics cooling. In fluid dynamics also we can apply PDE, aircraft design, weather prediction, medical blood flow analysis. In wave propagation, telecommunication, earthquake modeling, we are applying the partial differential equations. And in chemical diffusion also explains animal patterns like stripes and fingerprints. In population dynamics, the PDs are applying like a Fisher equation and a Fitius-Nagumo equation and Murray equation. In quantum mechanics, fundamental in the semiconductors, lasers, quantum computing, we are applying the partial differential equation. That the equation is not a Schrodinger equation, very, very important equation in quantum mechanics. Now we come to the fractional integrals. The basic the formula for Cauchy's formula for repeated integration is what? 1 by n minus 1 factorial integral 0 to x minus t whole power by n minus 1 f of t dt n belongs to n. Here, what is the fractional here? We remove the n, yeah, belongs to the natural number by alpha. Alpha may be the any fractional number. Instead of 1 by n minus 1 factorial, we have 1 by alpha factorial integral 0 to x minus t whole power alpha minus 1 f of t dt. Alpha does not belong to the natural numbers. Alpha is the what? Is a fractional number. Here, fractional derivative. What is the derivative formula? General derivative formula: d power alpha by dx power alpha x power k. What is the k factorial by k minus alpha factorial x power k minus alpha. Alpha belongs to the natural number. Here, when we introduce the whatever fractional derivative here, alpha is a fractional number. That is the fractional derivative. Fractional derivative, what a d power alpha by dx power alpha x power k. What a factorial become is the gamma function. Factorial will become the gamma function. Gamma of k plus 1 divided by gamma of k minus alpha plus 1 x power k minus alpha k greater than or equal to 0. So this is the fractional derivative. Introducing the instead of integer derivative, we apply the fractional derivatives here. And main two definitions of fractional derivatives and integrals is the Riemann-Liouville definition and the Caputo definition. Using these definitions, we are solving the fractional differential equations. And the Caputo definition we are mainly applied to solve the differential equation, because we can keep the initial and boundary condition as the integer order boundary conditions in Caputo definition. In Riemann-Liouville definition, we need fractional order boundary conditions or initial conditions. So it is best to apply Caputo definition to solve the fractional derivatives and integrals. What is reaction diffusion equation? Reaction diffusion equation is contain the reaction term and diffusion term. Here the general form of reaction diffusion equation is equal to dou u by dou t is equal to d into diffusion coefficient is missing here, d into dou square u by dou x square plus r of u. Here r of u is what? Reaction term, and d is the diffusion coefficient. D should be introduced between before dou square u by dou x square. Dou u by dou t is equal to d into dou square u by dou x square plus r of u. Here u of x, t, any substance concentration that which is diffusing, and x is the position variable, that is spatial variable, and t is the time variable, and d is the diffusion coefficient, and r of u is the reaction term. Why we are focusing now in a reaction diffusion equation? What is the reason? Reaction diffusion equations are used to model various physical, chemical, and biological processes. Examples include chemical reactions, population dynamics, heat conduction, and biological pattern formation. And in chemical engineering, reaction diffusion equations describe how reactants interact and diffuse over time, which helps in designing reactors and understanding chemical processes. In biology, reaction diffusion equations model processes such as cell signaling, neural activity, and the spread of diseases. And what are the important of RDs? Solving reaction diffusion equation with high accuracy is critical in predicting outcomes, optimizing processes, and making informed decisions in science and engineering. Many natural systems exhibit nonlinear behavior. Actually, in natural system physical problem, many physical problems are not linear. They exhibit the nonlinear behavior, which makes their modeling challenging. Fractional order models offer a more accurate representation of memory effects and anomalous diffusion processes that standard integer order models may overlook. I will explain what is anomalous diffusion processes. Traditional methods may fall short for complex nonlinear systems, motivating the use of wavelet methods for improved accuracy and computational efficiency. What is the anomalous diffusion? Consider the fractional diffusion equation here. Dou power alpha u by dou t power alpha. Here alpha is the fractional order derivative. Here the fractional order time derivative is introduced, d into dou square by dou x square plus reaction diffusion equation. Here fractional order, we can apply fractional order time derivative, fractional order spatial derivative, or both fractional order time derivative and the spatial derivative. Here we consider the fractional order time derivative. What is the anomalous diffusion process? T power alpha has non-linear relationship with time, while standard diffusion behavior has linear relationship. In standard diffusion, under what is diffusing substrate U has the linear relationship with the time variable. Linearly, if time varies, the what a substrate concentration also varies. That is the linear process. But in the anomalous diffusion process, here when you apply when you introduce the fractional derivative, it is the non-linear relationship. The diffusion process has the non-linear relationship with the time. Yes, for standard diffusion, alpha is equal to 1, integer or fractional derivative. For anomalous subdiffusion, alpha should be less than 1. And for anomalous superdiffusion, alpha should be greater than 1. For anomalous superdiffusion, here it should be greater than 1, not less than 1. Anomalous superdiffusion, it should be greater than 1. Anomalous subdiffusive behavior is associated with highly damped particles in random potential. Anomalous superdiffusion behavior is associated with a low damping with periodic potential. And the examples for anomalous subdiffusion is protein diffusion within cells and diffusion through porous media. And anomalous superdiffusion is associated with the turbulent fluid flow. And a few examples of a reaction diffusion partial differential equation models. Fisher equation, very famous equation for in population growth. Here the reaction term is u into 1 minus u. U is the what a substrate that are diffusing. The concentration of the substrate which is diffusing. Peters-Nagmo equation, here the reaction term is u into 1 minus u into u minus alpha. Hodgkin-Huxley equation, here the reaction term is u square into 1 minus u. Newell-Whitehead equation, reaction time is u into 1 minus u square. The mathematical modeling derivations are available. You can check it in Google. What are the applications of this equation? Fisher equation describes the advance of advantageous genes, population growth model, and Peters-Nagmo equation describes diffusion of electric potential across the cell membrane. Hodgkin-Huxley equation describes the diffusion of action potential in neurons, and the Newell-Whitehead equations describes Rayleigh-Benard convection. And some semi-analytical methods we have to compare with the wavelet methods. Odomian decomposition method, ADM variation iteration method, homotopy perturbation method, homotopy analysis method, differential transform method, and method of lines. And MATLAB simulation also we can compare our wavelet solutions. How wavelet transform emerged? We know about the Fourier series. In 17th century, Fourier series were found by the Joseph Fourier. What is the Fourier series? The Fourier series is used to represent the periodic function, breaking them down into sine and cosine components of various frequencies called harmonics. Here we are so a function is given, that should be a periodic function. We project the function into the sinusoidal function, sine and cosine components. After projecting that mainly I want to say in mathematics we are called again f of x is the function. In engineering it is a signal. We are projecting the signal into the sinusoidal sine and cos functions to analyze the functions. What is the frequency content? What is the time factor? Everything. After analyzing for that we are applying the Fourier series. So for a periodic function f of t, mind that in mathematically we call it function, and in the engineering it is a signal. For a periodic function f of t with the period t, the Fourier, what is the periodic function? F of t plus capital T, period t is equal to again f of t. Sine and cos are periodic functions. Mind that. The Fourier series is f of t is equal to a naught plus sigma n is equal to 1 to infinity a n cos n omega naught t plus b n sin n omega naught t. Here omega naught is equal to 2 pi by t is the fundamental angular frequency. That is, this decomposition is crucial for analyzing periodic signals such as electrical circuits, sound waves, and mechanical vibration. Then there is an improvement goes to the Fourier transform, continuous Fourier transform, another evaluation from Fourier series. The Fourier transform extends the Fourier series to non-periodic continuous signals. Yeah, for its series is only applied to the stationary signals. Here it is a non-periodic continuous signals. We can apply Fourier transform, continuous Fourier transform. It transforms a time domain signal into its frequency domain representation using this formula. Many of you who engineering graduates know about that. In first year itself, they have studied the Fourier transform. F of omega is equal to integral minus infinity infinity f of t e power minus I omega t, and again the inverse Fourier transform, the formula is given. Here the continuous Fourier transform is used in signal processing, physics, and communication to analyze continuous signals such as seismic waves, sound waves, and electromagnetic radiation. These are the applications. After converting the function, a signal from time domain to frequency domain, we analyze the frequency content of the signal. Then again, we convert back to the frequency domain to the time domain using the formula f of t is equal to 1 by 2 pi integral minus infinity infinity f of omega e power I omega t d omega. Omega is the frequency representation. Then another improvement, then evaluation of the discrete Fourier transform. Here, real world signals are often sampled at discrete intervals. Here we are we are sampling the whole time interval. It is infinite in the continuous Fourier transform, but here we are sampling the discrete time intervals. The whole n time intervals, for example, the whole timeline t divided by the discrete time intervals with the length delta t. So n time intervals is equal to t by delta t, and we are taking in time interval that those time intervals are analyzing the signal frequency content of the signal in those time intervals. That is known as discrete Fourier transform. Computes the Fourier transform for discrete sequences. Here the formula is given for a sequence xn of length n. The DFT is defined as xk sigma n is equal to 0 to n minus 1 xn e power minus I 2 pi by n kn, and xk represent the frequency components of this sequence. And formula for the inverse DFT is also given. After converting the frequency domain, then again the signal is converted into the time domain again using the inverse discrete Fourier transform. And the DFT is fundamental in digital signal processing used in applications like image compressions, audio analysis, and spectral analysis of signals. Now, then another evaluation from the DFT. DFT is considered as a slow, so we need fast Fourier transform. Fast Fourier transform. Here the signal is what n is equal to delta by t in the discrete. Here we take n is equal to 2 power m signals only. The signals are sampled. The time domain is what taken as n is equal to 2 power m. So the intervals are what reduced. If intervals are reduced, that makes the Fourier transform what a fast Fourier transform. The DFT has computational complexity. O means operations. When n intervals are there, operations are n square operations, which can slow the large data sets. The fast Fourier transform FFT works by breaking down the DFT of a large data set into smaller DFTs of subsets of the data. And the FFT reduces the complexity of DFT calculations from n square operation to n log n operations. N log n operations, making it significantly faster for large data sets. Okay, it divides the problem into smaller and smaller pieces until it becomes simple enough to solve directly. This process significantly reduces the number of calculations. And fast Fourier transform is used in almost every area of science and engineering, from digital audio and image processing to solving the differential equation, simulating physical systems in quantum mechanics. And it is also what a limitation. Fast Fourier transform is also a limitation. This discrete and fast Fourier transform will only give the frequency content, no time information. Here time information is lost. What can we do? Then the scientists, mathematicians developed another one, windowed Fourier transform. And windowed Fourier transform clearly explain how we are shifting to wavelet transform. The windowed Fourier transform or short time Fourier transform is a modification of the Fourier transform to analyze the signals that vary over time. Here, the time information is also considered. Not only the frequency content of the signal, time information also can be calculated using the windowed Fourier transform. That is, we are analyzing the windowed part of the signal using the Fourier transform. We can analyze the windowed part of the signal using the Fourier transform. For 2 minutes, I'll take the water. The mathematical form of a windowed Fourier transform of the signal f of t is w of t comma omega minus infinity f of dou g of t minus dou e power minus I omega dou d dou. Here g of t minus dou is the window function that localize the signal in time. Here, what is the limitation in this window function? We cannot change the size of the window. We cannot change the size of the window. That is the limitation. That leads to the development of the wavelet transform. The WFT is useful for analyzing non-stationary signals such as speech, music, and radar signals. It is applied in fields like speech recognition, music synthesis, and biomedical signal analysis. What are the limitation? Why we develop wavelet transform is developed already. We have discrete Fourier transform, fast Fourier transform, and to get the time information, we have windowed Fourier transform. Why wavelet transform? Why we need the wavelet transform? But because we have limitation for the windowed Fourier transform. Windowed Fourier transform uses a fixed window size for all frequencies. This fixed window size limits its ability to analyze both low frequency and high frequency components efficiently. High frequency components need shorter windows for better time resolution. Low frequency components need longer windows for better frequency resolution. So the window transfer Fourier transform uses the same resolution for all frequencies, which limits its flexibility. Now we move to the wavelet transform. Then the wavelet transform is developed. What are the wavelet? The short time finite duration function. Wavelets are the short time finite duration. It has only the finite duration. In Fourier transform, in all Fourier transform, we are using the trigonometric function, cosine and the sine function. It is infinite functions. But here the wavelets are the it vanishes after a particular time. It vanishes after a particular time. That is known as the compact support. And these waveless functions are orthogonal functions, orthonormal functions, and it satisfies compact support, and it satisfies the multi-resolution analysis. Then only it will make the wavelet transform is so effective. And wavelet functions are short duration, finite energy, orthonormal functions, and this is the mother wavelet. Mother wavelet is given here, and modulus A whole power minus of is the normalizing constant, psi of t minus b by a. Here b is the translation parameter and a is the dilation parameter. And b is the we can in time scale what a time axis we can change the time using the translation parameter b. And in the frequency we can change the scale of the frequency using the a dilation parameter. So we can change the windowed function. We can change the size of the window using the translation parameter b and the dilation parameter a. Scaling parameter. It is related to scaling parameter is related to the frequency content, and translation parameter is related to time axis x axis, and in y axis it is the frequency content, and it is scaled and translated to form a basis for Hilbert space for square integral function. And the square integral function is the basis for the Hilbert space, and these wavelet functions are the square integral functions. Then only it satisfies the multi-resolution analysis. What are the genesis of wavelets? How it originated? In 1807, Joseph Fourier developed a method for representing a signal with a series of coefficients based on analysis of function. He used the sinusoidal function to represent a signal. And in 1909, Alfred Haar defined Haar basis function with compact support, vanish outside the finite interval. In 1980, Alex Grassmann and Jean Marlet derived a signal decomposing method into wavelet coefficients. And in 1985, Stephen Mallet developed a multi-resolution analysis using wavelets. 1988, Ingrid Davaches, a woman mathematician, used Mallet work to construct her own family of wavelets. And this, what now the definition of the discrete wavelets. And psi of k comma n is what a modulus of a naught whole power k by 2 psi of a naught power k t n into b naught. Here you what a the continuous wavelets are discretized into the discrete wavelets. Here it is discretized using the what here this time function is the discretized using the scaling function is the discretized using the a naught power k, and time function is discretized using n b naught. And best if we have k is equal to 2 and n is equal to 1, it is the best choose for the dyadic. It is the dyadic, and we can apply the wavelet transform for the to solve the differential complex differential equation. We are choosing the a naught k is equal to 2, a naught power 2, and b naught is equal to 1. Here a naught greater than 0, the scale parameter, b naught is the position parameter, that is the translation parameter. The continuous Euler transform is given 1 by root of a integral minus infinity to infinity f of x I star x minus b by a dx. F of x belongs to square integrable function that forms the basis in Hilbert space, and a greater than 0 is the scale parameter and b is the position parameter. The Euler transform overcomes the limitation of the windowed Fourier transform by allowing the window size to vary. This makes it a multi-resolution analysis tool that provides better time localization for high frequency components and better frequency localization for low frequency components. Unlike a windowed Fourier transform, the window size is fixed. Wavelets have a scalable window. We can change the size of the windows using the translation parameter B and scaling parameter A. And the wavelet transform uses shorter windows for high frequencies, better time resolution, and longer windows for low frequencies, better frequency resolution. The wavelet transform breaks the signal into wavelets, small wave-like oscillations that are scaled and translated across the signal, providing localized information in both time and frequencies. Some of the examples of discrete and continuous wavelet, discrete R wavelet, Legendre wavelet, Chebyshev wavelet, Matthew wavelet, Dabachi's wavelet. Now they are using the Hermite wavelet, Lucas wavelet, Bernoulli's wavelet. Many wavelets are there. Continuous wavelet, Shannon wavelets, Mexican hat wavelet, Hermitian wavelet, Morlet wavelet, and Beta wavelet. This is the multi-resolution analysis. This is more mathematical, and here the components of the square integrable functions are decomposed into the closed nested closed subspaces. uh, Vn minus 2 contained in Vn minus 1 is contained in V minus 1, contained in V naught, contained in V naught as closed nested subspace, and V naught is the origin. By translating, so using the scaling function from the V naught, we can construct the other subspaces. These subspaces satisfy these properties, and the union of these subspaces is dense in L square R, and the intersection should be 0. And if f of x belongs to V naught and f of 2 power jx belongs to Vj, that is the scaling function. Sorry, yes, that is the scaling function. If f of x belongs to V naught and f of 2 power jx minus k belongs to Vj, this is the translation function. And here there is a scaling function pi of x minus k using this from one subspace V naught, we can construct the other subspace V1, V2, V3, here V minus 1, V minus 2, etc. And these are decomposition. The decomposition of the signal into close the vector space subspaces, and using the wavelet scaling function, we can decompose these subspaces, and we can analyze the frequency of the signal in these subspaces using the wavelet functions. And some example problem for coming to the application of the wavelets, Lan-Emden type equations, and if, I also given the citations also, and here the Emden differential equation non-linear, this singular differential equation d square y by dx square plus alpha by x dy by dx plus f of x comma y is equal to 0. Here ordinary analytical method we cannot use, because alpha by x, if x goes to 0, it will goes to infinity. If x goes to 0, it will goes to infinity. This is singular differential equation. So we apply the semi-analytical and wavelet methods, and boundary conditions are given here. Here, generally, the above equation, the heat conduction equation through a solid with heat generation source within the solid. The function f of x comma y represents the heat generation within the solid. If alpha is equal to 0, this alpha is equal to 0, it is a solid, is a plane. If alpha is equal to 1, that solid is a cylinder. Heat conduction in the solid is a plane when alpha is equal to 0. Alpha is equal to 1, solid is a cylinder. And alpha is equal to 2, the solid is a sphere. And this equation arises in astrophysics that describes the temperature variation of spherical gas cloud under the mutual attraction of its molecules and subject to the laws of thermodynamics. And it also describes the distribution of heat sources in human head, describes the steady state oxygen diffusion in spherical shell, models the thermal explosion in an infinite cylinder or sphere. Here we apply the shifted second kind Chebyshev wavelet, discrete wavelets we are applying, and the wavelet function is defined here. Here there are four components: K, N, M, T. M is the order of the second kind Chebyshev. Using the Chebyshev polynomial, shifted second kind Chebyshev polynomials, we are constructing these wavelets. T is the normalized time, and these wavelets are defined in the interval 0, 1. And this function is f of t is approximated from 0 to infinity to 0 to m. Here 0 to infinity, and it is cnm is what coefficient function, integral 0 to 1 omega of t f of t psi n of nm of t dt, and omega of t is the weight function root of 1 minus t square. And this infinite series is truncated to n is equal to 0 to 2 power k minus 1, and m is equal to 0 to m. This is the function approximation, and we construct the operational matrix of derivatives using this theorem. Using this formula, we are constructing the operational matrix of derivatives, and using this operational formula, we can construct the following the operational matrix of derivatives. D is equal to 0, 0, 0, 4, 0, 0, 0, 8, 0, and D square is equal to 0, 0, 0, 0, 0, 0, 32, 0, 0. And the wavelet matrix is psi of x root of 2 by pi is equal to into 2 80 my second row 80 minus 4, third row 32 t square minus 32 plus 6. We are going to find the wavelet coefficient. These are known as the connection coefficient C0, C1, C2. Using the connection coefficient only, we can analyze the signals, and we have to find that using these matrices, this differential equation is what converted into the set of nonlinear algebraic equation using the collocation point x is equal to 2 minus root 2 by 4. And for example, this equation is solved using the wavelet method. The nonlinear singular boundary value problem, which arises in the study of distribution of heat sources in human head, and this is the Lambda equation of the second kind. Here alpha is equal to 2. The right hand function is what f of x comma y is equal to minus e power minus y. With the boundary conditions, it is given, and we are applying the wavelet scheme here, and using the collocation point, the waveless complex differential equation is converted into this set of differential algebraic equation. Differential equation is converted into algebraic equation, and boundary conditions also converted into algebraic equation. We have three algebraic equations, non-linear, but normally we can using the traditional method we cannot solve this algebraic equation. These are non-linear, and using the numerical methods, many numerical methods are available to solve the algebraic equation. And using the MATLAB also we can solve this algebraic equation. We find the connection coefficient C0 0.1578, C1 and C2, and we can construct this solution. Y of x is equal to minus 0.1184 x square plus 0.3522. So the connection coefficients are very important. We have coefficients, we have to find the coefficient, then only we can construct the solution. And using the shifted second kind Chebyshev wavelet, we can compare the solution with the semi-analytical method, VIM, variational iteration method. Variational iteration method, the x values varies from 0.1 to 1. For that, the solution of the shifted second kind Chebyshev wavelet, where k is equal to 0, m is equal to 2, and k is the scaling parameter and m is the shifting parameter. That's and we are using the different scaling here. K is equal to 0, M is equal to 2, K is equal to 1, and M is equal to 3. We have the solutions and that are compared with the variational iteration method. What are, both are what are both solutions coincide. Very low minimum error is there. Both solutions are coincide. This shows the efficiency and accuracy of the wavelet method. Another example here, and this is what developed by Scuri and Safi, and this with Lange type equation. This is also, this is here 1 by x alpha is equal to 1, right hand function side function minus e power y with the boundary conditions here. And here this equation has the exact solution. This equation has the exact solution. And here our solutions are compared with this exact solution. Absolute numerical error is very low. Exact solution is given. The varies from 0 to 1. For that, the exact solution and shifted second kind wavelet solutions are given. And absolute numerical also are given here. And a very low error here. So the S2 case, generally wavelet methods are very very powerful in what find the solution with great accuracy. And also with the computation time is very low here for the wavelet methods. We can avoid the complex integration and complex differentiation. Another example is given. This is the nonlinear singular boundary value problem. Describe the equilibrium of isothermal gas pair. And here also the exact solution is available. And here the graph is given. The upper curve is what for the exact solution, and the lower curve is for the shifted second kind Chebyshev wavelet solution. And the solutions are mostly coincide. The solutions are mostly coincide. And another boundary value problem, steady state action diffusion in a spherical shell. Here the right hand side function is given f of x comma y and alpha is equal to 2 with the boundary conditions. Here also the shifted second kind Chebyshev wavelet method solution is compared with the homotopy perturbation method solution, semi-analytical method solution. The curves coincide. And like that, Legendre wavelets also. These are the what a Legendre wavelet function, and also function of approximation again. Again, we are using the theorem to find the operational matrix of derivative using this formula. We find this operational matrix of derivative for the Legendre wavelets. Connection coefficients are C0, C1, C2. Here we solve the kinetic model for simple Michaelis-Menten kinetics in chemical reaction, chemical kinetic reaction. For substrate concentration, the mass balance differential equation is given here. D square C by dr square plus k minus 1 by r dc by r minus pi square into c by 1 plus psi b c is equal to 0. Here the what is the R denotes the dimensionless particle radiation. In porous catalyst, the chemical reaction takes place. Well, C is the diameter substrate concentration. How the substrate concentration varies, and the pi is the Thiele modulus, and psi b is the absorption parameter. The shape of the immobilized catalyst is indicated by K, which for slabs, spherical, and cylindrical pellets respectively varies from 1 to 3. Here the initial values are given. The effectiveness factor of a catalyst particle can be also determined using this formula, and the substrate concentration profile using the wavelet method and the Taylor series method. They are compared with Adamian BW is a Bernoulli wavelet method is compared to the solutions of TSM Taylor series method, ADM Adamian decomposition method for various values of the Thiele modulus pi. And the effectiveness factor is also computed using the wavelet for the various values of the absorption parameter, and for the Thiele modulus varies from 0 to 1. And when Thiele modulus increases, the substrate concentration inside the catalyst will decrease. All the results we can infer from the solution, wavelet solution. When Thiele modulus is very important in the chemical reaction, Thiele modulus increases, the effectiveness factor will decrease in all the cases. When substrate concentration, the bulk increases, diffusional restriction decrease. The effectiveness factor is maximum at lower values of Thiele modulus for all values of absorption parameter. These results are founded from the wavelet solutions. And now come to the partial differential equation. And these are Fisher equation, population growth, Fisher equation, dou U by dou T is equal to dou square U by dou S square. This is the reaction diffusion equation. A into U into 1 minus U. U of x comma T is the population concentration, X the spatial variable, T is the time variable, D is the diffusion constant. A is the intensity of population growth, and AU into 1 minus U is the reaction term. It denotes the nonlinear population growth rate. And it is the population dynamics this equation is encountered in. And the example of Fisher equation involving the linear diffusion, nonlinear growth takes the non-dimensional form here. Dou by dou T is equal to dou square U by dou square A or alpha U into 1 minus U. The initial condition is given, and using the wavelet method, we can solve those equations, and compared with homotopy analysis equation, the absolute error is given. So you can watch that these absolute errors are low. For x varies, we take 0.25, 0.50, and 0.75, and the t varies from 0.5, 1, 2, 5. For these values, the wavelet Legendre wavelet method solution is computed, and it is compared with the homotopy analysis method, semi-analytical method solutions. And here we take the time fractional Fisher equation. Instead of integer derivative, it is a fractional order derivative is introduced. Alpha is the fractional order derivative. Already I told about the anomalous superdiffusion and anomalous subdiffusion. If alpha less than 1, it is the subdiffusion. Diffusion speed is very low. And superdiffusion, the diffusion speed is fast. Here alpha with the initial condition is given. This is the time fractional Fisher equation. When alpha is equal to 0.5, when alpha is equal to 0.5, we have the solution for using the differential transform method. That is also semi-analytical method. It's already available in literature. Using the Legendre wavelet method, we find the solution for various values of x and t, and those solutions of both methods, DTM and LLWM, are compared, and absolute error is given, and very what negligible. Absolute error is negligible here, 0.0008 and 0.007. So negligible absolute errors. Both it shows the what efficiency and accuracy of the wavelet methods. Another equation, Fittius-Takamo equation, it is what already it is a neuron biology. It models neuron distribution in the cell membrane, and the Fittius-Takamo equation is given with a highly nonlinear term is given here. Highly nonlinear term U into U minus alpha into 1 minus U with the initial condition is given. And here the closed form solution, not the exact solution. And the homotopy analysis method, we can find the series solution, and it can be written in the closed form. By the hand, we find the solution for the above Fittius-Takamo equation in the closed form. It is given already, it is in the literature. Now we apply the here the time fractional Fittius-Takamo equation also introduced here. Instead of integer derivative, it fractional order derivative is introduced with the initial conditions. These mathematical models are not just written, it is what developed by the mathematician and engineers, basically based on the physical problems. These initial conditions also they developed by the engineers and mathematicians. So we are applying the wavelet methods to solve that. We know the we are focusing the we are imposing the effectiveness and accuracy of the wavelet methods. And the time fractional Fittius-Takamo equation is given here, and here it is solved using the Legendre wavelet method. And those solutions are compared with the homotopy analysis method and Haar wavelet method. So already in the equation is solved using the Haar wavelet method. It is also already in the literature. And homotopy analysis method solutions are given for various values of x and t. And these solutions are compared. Mostly coincide. These solutions are mostly coincide. You can watch from this table. Now we come to the conclusion. The wavelet method demonstrated in this presentation are effective in handling both integer and fractional order models. They provide a highly accurate solution for reaction diffusion equation which model real-world phenomena. Whether the ordinary or partial differential equation, wavelet methods can efficiently approximate solution with complex boundary and initial conditions. Their adaptability makes them applicable across various scientific and engineering fields. The wavelet methods offer advantages over traditional numerical methods like Rangi-Gupta, especially in terms of computational efficiency and accuracy in solving fractional order equations. Wavelet-based numerical techniques continue to show potential in advancing the accuracy and computational efficiency of scientific modeling. Their further development will contribute to solving more intricate and nonlinear models in a wide range of scientific disciplines. Thank you very much.
Yeah, thank you, sir. Thank you so much for this wonderful presentation. So I have some questions here.
Ah,
So, should I ask the questions? Yeah, okay. So the first question, how can wavelet methods be further enhanced to improve the accuracy of modeling highly nonlinear systems in the field like climate science or finance?
yes, we can apply any nonlinear differential equations. We can apply the wavelet methods. The non actually we are making the differential equation to the algebraic equation, nonlinear differential equation to make the equation as the algebraic equations that make the process easily. We can in finance in any subject we can apply the wavelet methods. Here,
Okay.
there are two types of Euler method. Here I am describing Euler methods of operational matrix of derivatives. And the operational matrix of integration is also there to solve the complex differential equations. So using
Okay.
the situation, we can choose the Euler methods.
Okay, thank you, sir. Sir, what future advancements in computational power and algorithms are expected to make wavelet-based methods more accessible for real-time data analysis?
Yes, sir. Future many development methods are what developed, and it is also using the signal processing, image processing. Engineers are using the wavelets. Here I am describing how to solve the mathematical model using the differential equations. Many applications, wavelets have many applications in signal processing and image processing. Mainly, many applications, signal processing and image processing, and they are. It is a developing field. It is a developing field.
Yeah, okay. So, in what ways can wavelet theory be integrated with artificial intelligence to automate and optimize the process of solving complex mathematical equations?
Yes, sir. But artificial intelligence, what do you mean? What do you expect from me actually?
So, what ways can wavelet theory be integrated with artificial intelligence?
Yes, sir.
Oh,
Artificial intelligence means what do you mean here?
yeah. So, artificial intelligence to automate, optimize the process.
Yes, sir. We can find the computer program, computer algorithms for the Euler methods. Applying the
Okay.
computer algorithms, we can solve the differential equations. We can develop computer algorithms.
Okay. So okay, sir. So thank you, sir. So my final question.
Uh,
So how good future developments in fractional wavelets revolutions the modeling of biological systems is governed by fractional differential equations.
Yes, fractional. It has a great future for developing the fractional wavelets. Integer order wavelets are developed now. Fractional order wavelets are also developed. They are what a Rees fractional derivative and some other fractional derivatives are there. And using that, we can solve the complex fractional differential equation, which models the physical phenomena. It is a developing field.
Okay. So thank you, sir. Thank you for the useful answers. So the answers are very useful. I hope the access and that the participants can understand about that. So it's finally it's with great gratitude that I take this opportunity to extend our sincere thanks to Professor Dr. R. Rajaraman for sharing his profound knowledge with us today. His insightful presentation on wavelet methods and their role in solving complex mathematical equations has certainly expanded our understanding and inspired new avenues of thought in scientific modeling. So we deeply appreciate the clarity and depth with which he explained such advanced concepts. So, Dr. Rajaraman, your dedication to the field of mathematics and your willingness to guide and share your research with us today have truly been invaluable. So, your extensive experience and innovative approach to tackling non-linear and fractional differential equations through wavelets have opened up exciting possibilities for the future exploration. On behalf of everyone here, I would like to express our heartfelt thanks once again. We are fortunate to have had the opportunity to learn from you, and we look forward to seeing the continued impact of your work in the academic and scientific communities. So, thank you, Dr. Raja Raman, sir. Thank you so much.
Thank you so much for giving me the
Sir,
valuable
and
input.
just 1 minute, sir.
Uh,
Sir, can you able to see the virtual memento?
yes, sir.
Okay, sir. So, on behalf of Mastering Up, we present this virtual memento as a tribute to our guest speaker, Dr. Rajaraman. Your insightful contributions have enriched our knowledge and inspired us profoundly. So, this token of appreciation symbolizes our gratitude for your expertise and dedication. So, thank you for sharing your wisdom with us and shaping our understanding in profound ways. So, thank you, sir. Thank you so much.
Thank you so much.
Yeah, thank you, sir.